Good afternoon, everybody. It's a pleasure to have all of you in the Logics in Quarantine seminar. On behalf of the Brazilian Logic Society and the Logic Interest Group of the Brazilian Computer Society, I'd like to thank very much Professor Paulo Oliva, who accepted our invitation. Paulo, it's up to you. Thank you very much.
Thank you very much, Bruno and Petruccio, for the invitation. So this is based on some joint work that I did with Martin Escardo over a few years, I think starting in 2007 or 8. And I think we actually started working while we were in the WOLIC meeting in Rio. So we are both Brazilians living in the UK, but we started working in Brazil. And so I could also maybe use the title for this talk, 5 definitions and lots of examples, because that's what it's going to be. So I'm going to give you 5 definitions. And for each definition, I'll try to motivate the definition with several examples. And then conclude with some remarks for after each definition. So I asked Bruno to relay any questions that you might have. So it's really important that you try to follow. If you don't follow the first definition, it's going to be really tricky to follow the rest of the talk. So if you don't understand already the first definition or the second, feel free to stop, post on the chat, and Bruno is going to bring it to my attention so that I can go back and try to clarify. Okay. So this is mainly about what I would call continuation operators. Okay, so this is going to be the first definition. And before I give the definition, let me just say that this has a lot of connections to logic, and a lot of the examples will be from logic. And I came across these continuation operators when doing what's called proof mining. So when trying to analyze proofs in mathematics to extract computational content from these proofs. But then when talking to, when I was attending Martin's talk in WOLIC in Rio, I noticed that the constructions that Martin was using in computable topology were very similar to the ones that I was using in proof mining and proof interpretations. Then we got together and realized that actually this kind of construction, this kind of operators and the corresponding constructions, they appear quite often in other areas. And I'll give you some examples from game theory and also fixed point theory. So hopefully this will be kind of the motivation for considering such operators. Okay. So as I said, the plan for the talk will be 5 definitions. So for each definition, there will be lots of examples, followed by some remarks. And as I said, if you do not understand the definition, or if the examples are not clear, feel free to stop, write on the chat, and Bruno is gonna bring this to my attention. So the first definition, as I said, is that of a continuation operator. Sorry about this. So what we are going to call a continuation operator is a function on functions. So it's a function of what we call a function of type 2. So if you can see my, oh, sorry, I don't think you can see my mouse. But on the first line, can you see my mouse? I cannot see my mouse.
Yes.
So that's strange. So let me try again. Oh, now I can see. Okay. So what you see here is a function from x to r. And you can think of x and r as types, like in type theory. Or you can think of x and r just as sets. Okay. You can even think of x and r as formulas using the Curry-Howard correspondence. Okay. So x arrow r would then be either a function from set x to the set r, or the type x to the type r, or the implication x implies r. If you're thinking of formulas, then these operators would be proofs. So proofs of formulas of this type. Okay? But let's stick to the idea that these things are types. or sets. And we think of these as functionals or operators because they operate on a function. So they take a function as an input and they return a value. And I'm going to use an abbreviation for this. I'm going to just call this k of x with subscript r for this type. Okay, so let's look at the first example from logic. So the first example, for the first example, I'm going to take r to be the type of booleans. Okay, so if we take r to be the type of booleans, then k x boolean has this type. Okay, so it's x arrow booleans to booleans because I've taken r to be the booleans. Now, a function into the booleans can be thought of as a predicate, right? Because a predicate, if you think of the characteristic function of a predicate, is exactly a function from some set of type x to the booleans. So that means that things of the type predicate arrow boolean are exactly the quantifiers. Okay, so the first example of a continuation operator that I'm going to have is the quantifiers, the for all and the exist. So the for all and the exist, thought of as functions from x arrow booleans to the booleans, are continuation operators. And you might be thinking, how can you think of usually you think of the extension quantifier as just a language construct. But if you're able to take kind of formulas and form functions using this lambda notation, then there exists x is smaller than 10, is nothing more than the characteristic function for this predicate, and given applied to this existential quantifier operator. It's the same with the for all. So for all can also be thought of as an operator because you can think of the predicate x bigger or equal to 0 as a function lambda x bigger than 0. And you can see that this has exactly the type x arrow boolean. So I really hope that this is clear, because if it isn't, you should shout now before I proceed to the second example, okay? No shouts? Okay, so...
No question.
No question, huh? Okay, so the second example of a continuation operator that I'm gonna show you is from analysis. So suppose that we now take x to be the unit interval, and we take r to be the real numbers, okay? Now we look at what this type becomes, and it becomes functions from 0, 1 to the reals into the reals, okay? Examples of things of this type are inf and sup, okay? The infimum and the supremum of a function, or the integral operator, okay? So if you have a function from the unit interval to the reals, you can look at the integral of this function. If you have a function from 0, 1 to the reals, you can look at the infimum or the supremum, okay? Again, so hopefully this is clear. This is the second kind of class of examples. So we had two examples in the first one, the exist and the for all. And now we have inf, sup, and integral as examples of continuation operators. Third example will come from game theory. So now think of X as the set of strategies in a game, okay? So any game, think of any game and think of X as the set of strategies. And think of R as the set of outcomes in the game, okay? When I say strategies, I really mean strategies for like all strategies. So if you're thinking of a two-player game like chess, strategy would really be a combination of the strategies of both players. So the strategy for a chess game is a pair of strategies for white and strategies for black. And the outcome is either a draw, black wins, or white wins. Okay? But in game theory, it could be anything. It could be maybe payoffs for the different players. It could be simply a win or lose with no draws and so on. Then what are functions from strategies to outcomes? Well, I claim that you can think of the description of a game as exactly a mapping from strategies to outcome, okay? So to define a game, it means to say for any given strategy what the outcome of the game is. Okay? So X arrow R, in this case, it can be thought of as a game. And then when you think of this type again, X arrow R, this is one example of a continuation operator in this setting, is something that takes a game and calculates the optimal outcome of the game. That means, what is the outcome of the game going to be if the players play optimally? Okay, I hope that is clear. So given any game, you can say, suppose that the players play optimally, what is going to be the outcome of the game? And that is another example of a continuation operator. Fourth example comes from fixed point theory. So in this case, I'm going to take X to be the same as R. Okay, so if you take X to be the same as R, then K of X subscript X becomes X arrow X arrow X. And in this case, something of this type is the fixed point operator. Okay, so the fixed point operator takes a self-mapping, a mapping from X to X, and returns a value in X such that P applied to that value is the value itself. Okay, so it calculates the fixed point to the function P. Okay, so this is the first definition, as I said, and just a few remarks. So normally, as you have seen, if you are in a particular domain, you are going to fix R and you're going to look at various values of X. So when we're talking about logic, R was always the booleans. Okay, so when we're talking about the quantifiers, R was the booleans. And then if we wanted to quantify over different types, like let's say we want to quantify over the integers, then we take X to be the integers. If you want to quantify over the reals, we take X to be the reals, but the type R is fixed, is the booleans. If you are in analysis, again, R is usually taken to be the real numbers, and then you can change X depending if you're integrating over the unit interval or any other compact set. The second remark, for those who know already a bit about monads, is that K is nothing more than the continuation monad. Okay, so if you haven't heard about the continuation monad before, don't worry, this is just a remark. It's not needed for the rest of the talk. But if you have heard of the continuation monad before, and that's what it is. So this type parameterized, when you fix R, becomes a monad in X, because you have maps like this. You have maps from X to K of X, and here it is. And you have maps from K of X to K of X, and here it is. Okay, so that makes K a monad, and it's the well-known continuation monad. The second definition I'm going to give you is that of sequencing continuation operators. So the idea is that once you understand what these continuation operators are, we can ask ourselves, what can we do with them? Okay, and one operation we can do with them is to sequence these continuation operators. So here is the second definition. So it's going to get slightly more and more trickier. So do stop me if you have questions. So given continuation operators K of X and K of Y, and as I said, I'm always going to think of R as being fixed, we can define the sequencing of phi and psi as a new continuation operator, but now on the product space X times Y. Okay, and here's the definition. So while you can try to parse this definition while I give you some concrete examples. So again, let's go back to the example of logic, and let's take two different continuation operators. So let's take a continuation operator to be there exists X over some type X, and there exists over some type Y. Okay, so these are two continuation operators like these ones. And what does it mean to sequence there exists X and there exists Y? Well, for that, I'm going to need a predicate on a binary predicate, so a predicate on X times Y. So think of this as a formula on two variables, X and Y. So to sequence x and y according to this definition here, if you just unfold the definition, or if you just plug in phi and psi for there exists x and there exists y, you get this. Okay, so to sequence there exists x and there exists y on a binary predicate is nothing more than to existentially quantify over x and then existentially quantify over y, which we normally write like this. Okay, so sequencing these continuation operators in logic is nothing more than just putting quantifiers together. Okay, and it's the same for if you had an exist and a for all. So the second example says, suppose that you have a for all over the natural numbers and an exist over the natural numbers. Again, these are two continuation operators. And now let's take a concrete binary formula on two variables. Let's say m bigger than n. Okay. Then sequencing for all n exist, and then this gives me a predicate, a continuation operator over n times y, which I can then apply to the predicate q to get the formula for all n that exists in m bigger than n. Okay. So what you are realizing so far is that I'm not telling you anything new. I'm just giving a different name for the things that you already know. Okay, so you already know about quantifiers, you already know about inf and sup and integral and fixed point operators and maybe even game theory. And you know how to put quantifiers together, but I'm just giving these a name. So see, so these are now continuation operators, and doing this is sequencing these operators. Okay. If you go to analysis, it's the same. So sup and integral are continuation operators. And if you want to sequence them, you need now a real valued function on the product space. Okay, so because once you sequence two quantifiers over x and over y, you get a new quantifier or a new continuation operator over the product space x times y. And here it is an example. So let's say that my function takes two numbers in the unit interval and just multiplies them. So what does it mean to sequence the integral and the sup and then apply to q? Well, it's what you've always been doing in analysis. It means to take the integral of the sup of some function. Okay, so this would be the integral over the variable x of the sup over the variable y of the function x times y. Okay, again, nothing new. It's just giving you a different kind of way of looking at things that you already know. That's the second definition. And the remarks I want to make here is that, of course, you can iterate this binary operation to sequence an arbitrary number of continuation operators. Okay, and we know how to do this in logic. So if you can put not just two quantifiers together, you can put any number of quantifiers together. This sequencing operator is associative, but is not commutative in general. Okay, so the existential quantifier commutes with another existential quantifier, but not with the universal quantifier. Okay, so this is associative, but not commutative. And it does have a neutral element if you have the unit type. So if you have a type with one value, and if you identify x times 1 with x, then this lambda p applied to the star is actually a neutral element for this associativity operator. Okay. What you get is a kind of a monoid, a non-commutative monoid. So these are the two definitions. So now let's, as I said, I only have 5 definitions, but they do get slightly trickier. So I'll try to go slower as I move along. So the third definition is that of a continuation operator, which is attainable. Okay. So we have looked at several continuation operators. Now let's look at which of them are attainable. So what does it mean for a continuation operator to be attainable? So I said a continuation operator, phi, is attainable if for each p, so for each function from x to r, there exists a value A such that quantifying over P is the same as applying P to that value A. Okay, so this is something that you probably haven't seen before, and so that's why I said I would try to go a bit slower here. Okay, so let's just look at the things that we have seen, and let's see which of the quantifiers or which of the continuation operators are attainable. Okay, so this is probably the place where, if this was a normal lecture, I would try to ask the audience and wait for some answers. But here is a bit difficult because all I can see is my own screen, and it could be that you're already falling asleep. But anyway, so if you are still awake and trying to follow, think about the existential quantifier. Is it attainable? So is it the case that given a predicate on one variable, and there is always a value A such that there exists x p of x is the same as p of A? Okay, and I hope some of you said yes, because that is indeed the case. So giving a predicate P, assuming X is a non-empty set, of course, right? Because if X is empty, then we can never hope to find such A. But assuming we are working with non-empty types, then yeah, given any predicate, there is always a value such that if there exists X P of X is true, then P of A is true. Okay, because, well, if giving a P, if there is an X such that P of X holds, then we can just take that value to be A. But the more interesting observation is that if there isn't any X for which P of X holds, then any A will do. Okay, because this is going to be false, and this will be false as well, and this will still be an if and only if. So the existential quantifier is attainable. Okay, so that means existentially quantifying over predicate is the same as just checking the predicate on a single value. Okay, this is quite impressive, I think. It's difficult to come up with this value, but it's good to know that it's possible. Okay, now how about the universal quantifier? Okay, so is the universal quantifier attainable? Is universally quantifying over a formula, could it be equivalent to checking the formula on a single value? Okay, now this is the place where it starts to become a bit counterintuitive, because some of my logician colleagues, when I asked them this in a talk, they immediately said, no, this is true for the exist, but it's not true for the universal quantifier. But unfortunately, it is true for the universal quantifier as well. And this is what is known as the drinker's paradox, okay? Because it's kind of the same reasoning as for the exist in the previous slide, because you say, well, either P holds for all X, in which case you can take A to be anything. Well, this is going to be true, and this is going to be true as well. Or P doesn't hold for all X. So that means there is an A for which P doesn't hold, and we can take that A to be our witness, because then this will be false, but so will it be this. So it will be this. Okay, so once for all X P of X is not true, that means there is an A for which P of A is not true as well. Okay, so the universal quantifier is attainable, which means universally quantifying over predicate can be reduced to evaluating the predicate at a single value as well. How about the sup? Okay, so we look at the sup in analysis, taking the supremum of a function. Is that attainable? Okay. So that means, is it possible that doing the sup, calculating the supremum of a function is the same as evaluating the function at a particular value? Well, here it becomes a bit more subtle, because it is indeed true if you are working with continuous functions on a compact space like this, okay? Because that is exactly the extreme value theorem. Okay, so the extreme value theorem says that a continuous function does attain its infimum and its supremum on a compact space. So it is indeed true that the infimum of a function is the same as P applied to A, where A is the value where that infimum is attained, okay? So it turns out that the supremum and the infimum are also attainable continuation operators. Okay. How about the integral? So is the integral attainable? So is it possible that integrating a function is the same as applying the function to a particular value? Again, it is, if you're working on continuous functions on the unit interval 0, 1, by the intermediate value theorem. So the intermediate value theorem will say that the function will attain any value between its infimum and supremum in that interval, and in particular is going to attain its median value. And the integral on the unit interval is exactly calculating the median of a function, the average. So the integral on that space is also attainable. Finally, how about the fixed point operator? Is it attainable? Is it true that calculating the fixed point of a function is the same as applying the function to a particular value? Well, it is by definition, because the fixed point of P is equal to P applied to the fixed point of P. So in this case, the witness A is actually a fixed point of P. Okay? So the fixed point operator is, again, an attainable continuation operator. Okay.
Paulo?
Yeah?
We have a question from Valeria. Why the word attainable? Because for quantify it seems odd.
Why is it attainable? I think probably the example that justifies this is the supremum one, because you say that a function attains its infimum if there is a value for which the infimum is obtained, and a function attains its supremum if there is an x such that f of x is the supremum. Okay, so here is attainable in the sense that there is an a such that the function, the value of the quantifier is attained at that point. So you can think of this point A as the point where the value of the quantification is attained. Is that okay? I hope that's okay, Valeria.
It is, Paulo. It's pretty good.
Good. Any more questions?
No, I think. I mean, I do have another question, but I'll wait a little bit longer to see if it comes up.
Okay, good. You might be wondering, is everything attainable? So not all continuation operators are attainable. I mean, these are the common continuation operators, and they all turn out to be attainable. But of course, there are non-attainable quantifiers. Otherwise, this wouldn't be an interesting definition, right? So, for instance, a constant continuation operator, so let's say lambda p true, that always returns true, is not attainable, okay? Because if I give it the constant false function, the quantifier is going to say true, but there is no value for which lambda x false gives true. Okay? So a trivial quantifier, like a trivial continuation operator like this, is not attainable. Okay, so to be attainable is something quite special. This was the third definition. Any questions? Any other questions other than Valeria's before I proceed to the last two? No? So let's move to the fourth definition, which is that of a selection operator. Okay, so we talked about continuation operators. A selection operator is very similar. Okay, so for a continuation operator was a function from x to r to r. A selection operator is a function from x to r to x. Okay, so very similar, just the final result is not an r, but is an x. Okay, so an example from logic would be Hilbert's epsilon terms. Okay, so the quantifiers will tell you whether the predicate is true or not, whereas the epsilon terms will try to find a witness for which the predicate is true, if it is true. Okay, so think of the So this is I think an excellent analogy, because this is trying to select a point where the quantifier attains its value. Okay, so in analysis, examples of selection operators or selection functions would be argmax and argmin. Okay, so we have seen that the maximum and the min, or the supremum and the infimum, are continuation operators because they return the infimum and the supremum of a function. But if you want to know where the function attained its infimum or its supremum, then what you need is argmax or argmin. Okay, so the argmin doesn't give you the supremum or the infimum of the function, but it gives you the point where that infimum or that supremum is attained. Okay, hope that is clear. So as you can imagine, I mean, as you probably guessed from my little equation here, is that continuation operators are attainable if and only if there is a selection function that produces that value, that witness. Okay, so for the continuation operator to be attainable, we saw that for every p we had to have a value a such that phi of p was the same as p of a. Okay, but if for every p there is an a, then there is a function that selects that a. So a continuation operator is attainable if and only if there is a selection function that picks the a out for any given p. The other remark I want to make is that any selection function will give rise to an attainable continuation operator like this. Okay, because if you can find the witness, in particular, you can find the value by applying p to the witness. Okay, so if you are able to find witness with the selection function, then applying p to the witness gives you a value, and that gives you a continuation operator. So in some sense, selection functions are more general than these attainable continuation operators. Any selection function will give you an attainable continuation operator, but having a continuation operator, which even if you know is attainable, might be tricky to find or compute its selection function. That's it. We are almost there. So the final definition is that of sequencing of selection functions. So we looked at continuation operators. We looked at sequencing of continuation operators. We looked at attainable continuation operators, those that for any p there is a value a such that phi of p is the same as p of a. And then we looked at selection functions which kind of try to pick that witness a given np. And finally, let's look at how to sequence selection functions. Okay, this is the last definition. But it's also the trickiest one. So apologies, and hope you are still following. So given two selection functions, 1 over x and 1 over y, and remember, we always think of r as fixed, and we try to range, to vary the values of x and y. So we are going to define its sequencing as a new selection function now over the product space. But why is this so much trickier than sequencing quantifiers? Because when we are sequencing quantifiers, all you have to produce is a result. So you have to produce an R. But here, what you have to produce is a pair of witnesses. Okay, so if you know how to produce witnesses for predicates over x, and if you know how to produce witnesses for predicates over y, how do you produce witnesses for predicates, for binary predicates, for predicates over x times y? Okay? And this is how you should do it. So what you should do is start from here. So let's start with the b. So what does the b do? So the function b says for any given x, I can take my predicate q, which is a binary predicate, and I can make it unary, because once I have x, this is now a unary predicate just over y. Okay, and delta is able to pick witnesses for unary predicates over y. So I apply delta to this and I get a witness. So this function b is really important because it gives me a witness y for any given x. Okay? But once I have this function, I can then turn the Q, which is a binary predicate, into a unary one. Because given an X, Q of X, B of X has an R value. Okay? And once I have a unary predicate over X, I can use my X selection function to pick an X witness, which I'm going to call A. Okay? And once I have that witness A, I can then use the function B again to give me a Y witness, which is a witness for that X valued A. Okay? It is a slightly convoluted definition, but that's what it is. And that's what makes it work. So what do I mean by make it work? Is that we can obtain this, which to me is a really amazing result, is that if you have two attainable continuation operators, so if you have a phi and a psi, and each of them are attainable by some selection function epsilon and delta, then when you sequence the continuation operators, that itself is also attainable, and it is attainable by the sequencing of their corresponding selection functions. Okay, is that clear? Please feel free to ask a question, because I'm nearly done. So if this is not clear, I can try to help. No question?
No questions by now.
All right. Okay, so this is really the main result I wanted to present. And to present this, I had to define continuation operators. I had to say what does it mean to sequence two continuation operators. I had to say what does it mean for a continuation operator to be attainable. I had to define selection operator or selection functions, and I had to tell you about the sequencing of selection functions. Okay, but once we have all these 5 definitions, we are able to state this result and try to see what it means. Okay, so what does it mean in all these different areas that I discussed in the beginning? So in logic, this is what allows you to do quantifier elimination in Hilbert's epsilon calculus. Okay, so if you think of the Hilbert epsilon calculus, you only have an epsilon term that allows you to get rid of one existential quantifier. Okay, but how do we make it quantifier free? Well, we just iterate this, right? So we say, if you can always pick a witness for one quantifier, you can then, if you have 2 quantifiers, you just pick a witness for the innermost one as a function of the outermost one, and then you make that a new predicate, and then you apply the epsilon term for the next predicate, and so on. So that iteration is exactly this product or the sequencing of selection functions. Okay, again, something that was already out there, but I'm just trying to give it a name and use this to relate these constructions to other constructions in other areas. Because, for instance, in game theory, people were doing exactly the same thing. So they were doing the same construction, but they were using it instead to calculate sub-game perfect equilibrium of sequential games using what they call backward induction. Okay, so backward induction is nothing more than what Hilbert was doing in his epsilon calculus, because what you are doing is you are looking at a sequential game, and then you are trying to pick optimal moves at each point, and then collate those optimal moves into an optimal strategy for the whole game. Okay, and this is done exactly by sequencing selection functions, as I showed in the previous slide. Going to proof mining, where I was working when I first met Marty, I was studying bar recursion, and this was used to interpret countable choice, give a dialectic interpretation to countable choice, and hence give a kind of a Gödel dialectic interpretation to full analysis. But the construction I was using there was exactly this one, just iterated not finitely many times, but countably many times. So if you just say, instead of having a finite number of selection operators or selection functions, suppose that you have an infinite number of selection operators, and you just iterate this binary sequencing operation a countable number of times. Okay? What you get is exactly what Spector came up with in the 1970s, and he called it bar recursion. Okay? It's a way to interpret countable choice. In fixed point theory, this is what people know as Becky's lemma. Okay, so if you have two spaces x and y, and they both have fixed point operators, you want to show that the product space or the product domain x times y also has a fixed point operator. How do you do this? Well, you just say, well, fixed point operators are selection functions. I know how to sequence them. So if I have a fixed point operator over x and a fixed point operator over y, if I sequence those fixed point operators, I get the fixed point operator over the product space x times y. And that's exactly the proof of Becky's lemma. Okay, is this construction that you see here, but phrased in the setting where epsilon and delta are fixed point operators. So that's really what I had to say. So I'm happy to go back and try to answer questions and clarify things if they were not clear. But that's all I had to say. Thank you.
Thank you very much, Paulo. So now we have some time for questions, remarks, or any comment you would like to make.
Let me try to see the chat.
Remember that we are recording this presentation. It will be available in the YouTube and other social media from the Brazilian Logic Society. So please manifestate yourself in the chat to make some kind of line. Paulo, primeira pergunta. Sorry. Paulo, first question from Hugo. Can you maybe tell us about the name continuation? I guess it came from functional programming, continuation model. Can you tell a bit about that?
Yeah, that's a very good question. I think I had plans to talk about this, but forgot. So thanks for. So why do we call this a continuation operator? So yeah, this does come from functional programming, because there the idea is that you think of these functions here, x arrow r, as contexts. Okay, so you think of x as the value you are presenting now. So if you think of a term context, then I'm just thinking if I'm able to write somewhere. Actually, I can try to do this. So can you still see my screen?
Yes, we can.
There is no whiteboard here, is there?
No, sorry.
No, there is no whiteboard. Okay, so I'll just wave my mouse. So a term context in programming can be thought of as a function, right? Because you think of, if you have a term with a hole, that is a function from the values you plug into that hole to the final value. Okay. Now, if you think of x as the values you are plugging into that hole, and r as the final value, then this context can be thought of as this function, and it's normally called the continuation. Okay. Is what's going to happen, is the computation that is going to happen after you produce the value at that point. Okay. And continuation operators operate on continuation. So if you are able to access that context, then you are able to do more in functional programming. Okay, so call CC in functional programming in Haskell is a kind of continuation control operator. So this is used for defining control operators. So if you are able to access the context or the continuation of the computation, then you can do more. Can maybe do things more efficiently. So there's, sorry, who asked this? Was Patricia? Hugo, yeah. So Hugo, did this answer your question? Okay.
Okay. So there's another question from Petruccio.
That's what happens when you change the booleans for other algebras, and this is adequate to model other quantifiers. And so again, that's a very good question. And in fact, if you try to read Martin's and our papers, we actually call these quantifiers. Okay, so because the existent for all are just two examples, but you can think of anything like this as a quantifier, and then there is this notion of generalized quantifiers of Mostovsky, and this exactly means anything of this type. Okay? Anything of this type can be thought of as a quantifier. The existent and the for all are just two special examples of quantifiers. Now, what happens if you change the algebra? So if you change the booleans to something else, then you get other kinds of continuation operators. So I haven't really thought about that, so I don't think I can say anything more. But as you can see here, that as we change that R, so if we had the booleans here, we got the operators on logic, we changed that R to be the reals, and we got inf, sup, integral, and then we changed that R to be X itself, and we got control operators. So if you change that R to be, I don't know, Heyting algebra, then these functions would be functions from X to some Heyting algebra. So it would be Heyting algebra valued predicates, maybe. Or if you think of fuzzy logic, you could change the booleans to 0, 1, and these would be fuzzy predicates. And then you can try to think of quantifications in continuous logic as still as continuation operators. So it would make perfectly sense. Yeah. Patricia, does that answer your question? So so what I would say is that if you're just modeling other quantifiers, like in Mostovsky sense, then you don't need to change the booleans. Okay. So the generalized quantifiers are exactly things of this type. But if you change the R to be other algebras, then you get into other areas, like in analysis or game theory.
There is also another question from Valeria.
Valeria.
2 questions.
Thanks, Valeria. One is about, instead of using booleans, using falsum. Does it still fit into this framework?
Because that's the original notion of continuation, right? When you say kind of X to falsum, that's double negation. And so I was wondering if this very specific instantiation still fits in the general framework.
Yeah. So this is exactly how I got into this. So I was looking at classical proofs and applying double negation translations. So you get, like, instead of there exists X, you get not there exists X. But then what you do is you apply what's called Friedman's trick, and you replace false by some existential formula that you want to witness. So in this particular case, in the case I was working with, R was exactly this existential formula that was being used for falsum. So it was the witness that you were trying to extract. So this exactly fits into this, because that's where I came from.
Right.
Okay. And attainable continuous composing looks like a composition. Is there a new category there?
I assume the continuations by themselves already make a category of sorts, because you were saying that we have an associative way of composing them, and an identity of sorts, right?
Yeah. So do we make it into a category? Because this K is a monad, so maybe if we look at the classly category, I don't know. I think you are the person I would ask. So there is certainly some nice structure there. Yeah. But I must say I'm not a category theory expert to be able to say what the category is.
Yeah, one more, if I may, just more.
Yeah.
Sorry, but the other thing is, you know, the pairs where the first component is A and the second component is B of A. Again, looks like a dialectical sort of thing, right? Or half of a dialectica, because it's just the side of the world where things work, where you don't have counterexamples coming back.
Yeah. So these selection functions, they arise naturally from the dialect interpretation of a double negation. And if you think of Kreisel's no counterexample interpretation, these are exactly selection functions, because the counterexample function is the P, and the no counterexample is the selection function that, given any P, gives you a witness. You know, so this is very, very related to the dialectica and the no counterexample. So Marcelo asked, is attainability related to the notion of satisfiability? So that is very interesting. So I gave once a talk about this where I presented everything in Haskell. And the first example I had was to use the product of selection functions to build a SAT solver. And this is exactly what's happening. So the selection function for the existential quantifier and the universal quantifier, they are trying to find witness. And if you apply,
that's what I saw the intuition behind it. So that's the reason for my question, actually.
Yeah, definitely. So you can, once you have selection functions for the existential quantifier and the universal quantifier, and you have, if you're quantifying over the booleans, like in a SAT problem, right? Then once you know how to find a witness for one boolean, then you can iterate that selection function and find a satisfiable assignment to a formula on any number of variables, by simply iterating the selection functions for each quantifier.
But you have some notion of order when you're composing. I know it looks like quantifiers, like if you start skolemizing outside and then everything is a function of what has come before.
Exactly.
For satisfiability, this is a more subtle, because it depends on your first choice, actually.
Yeah, definitely. So this is, as I said, this is definitely not commutative. So the way you and even when it is, like with the existential quantifier or with the fixed point operator, it might matter the order in which you do things. You might get different witnesses. Okay, even though they are witnesses, but you can get completely different behaviors depending on the order in which you do things. For instance, in Becky's lemma, you have a choice, because the problem is completely symmetric on two domains. So if you have two domains, X and Y, and they both have fixed point operators, you want to find the fixed point operator for the product space. Well, you can sequence those fixed point operators in two ways, right? Because the problem is completely symmetric. And they both give you a fixed point operator, but they might give you different fixed point operators.
Okay, thank you.
No, you're welcome. Thanks for the question. Elio said, can I think of sequencing selection as the nesting occurring in epsilon calculus when translating nesting quantifier? Exactly, yeah. So if you have a nesting of quantifiers in logic, and you want to apply the epsilon terms to eliminate those quantifiers, you have to do it in exactly this way, that in this way here. Okay, so if you have for OX there exists a Y, what you have to do first you have to say, well, for each X I know how to eliminate the Y, so I'm gonna create this function that for any X gives me the witness for the Y, and then I'm gonna use that function to build a unary predicate, which you can then use the other epsilon term to find a witness for the X. Okay? So the way you eliminate quantifiers in the epsilon calculus is exactly by the sequencing of these epsilon terms. So that's what I say, that this is nothing new. It's just something that just happened in different areas, and people are using it, and without realizing that they were doing the same thing. So this is kind of bringing together what people have just been doing in different areas by giving it a nice theory around it, and trying to explain what's going on. Does that make sense, Elio? Thanks, Elena.
Any other question? No. So thank you very much, Paulo. Really, Hugo has another question.
Yes, sorry. Oh, the difficulty of finding selection operator, like some kind of compute one. So when it's easy, when it's hard. So it was, I think I would say it was not easy to find selection operators for some domains. For instance, part of the work that Martin Escardo was doing was to show that the contour space is searchable, that you have a selection function for the contour space. Okay, this is a really difficult problem, and it's a really non-trivial result, but it can be obtained by the combination, by the sequencing of local selection functions. So you have selection functions for one Boolean, and that's easy. So what you have to show is that when you sequence those a countable number of times, that then gives you a selection function for the contour space, which is the countable product of the Booleans. Okay. So what I would say the power of this is that when you iterate it, it gives you highly non-trivial results.
Can I give you a theorem?
Yeah.
You have these operators that they take a function and give you something Boolean. So
Yeah.
if you have that the complexity of applying that function, mainly computing that function, then computing a selection operator must be that complexity non-deterministic. Like you can guess what the operator is, and then you apply that function and check if that's correct. So you are in that direction. So it's not difficulty, but the complexity of computing those things. So it's, well, if you think of it, it's kind of a trivial theorem, but that's in the direction.
Yeah, no, I see exactly what you mean, because you can say, well, computing phi of p, once we know that computing phi of p is the same as p applied to A, then if you can try to guess what A is, and you can efficiently compute P of A, that already, if this is a kind of if the values of A are kind of polynomially sized bounded, then that already shows that this phi of P is in NP, isn't it? So that's a very good,
which goes back to the SAT example that I gave. It's exactly that.
That's a very good point. Very good point. Yeah.
Thank you.
Sorry, Hugo, did I answer your question?
There is a comment from Hugo.
Oh, I was more wondering about the non-computable case. Oh, I see. Figure out how non-computable it is. Yeah, I see. Yeah, so it could be, I mean, you're perfectly right, that it could be that that this A exists, but is not computable, right? So it could be that, and it is, for instance, quantification over the reals, okay? So we know that existentially quantify over all the real numbers is attainable, but we don't know how to find a real number such that quantifying over all the real numbers is the same as checking that particular real number. That's definitely not computable. So there are definitely several examples where this is not computable. And I think this goes back I would say, to the work of Martin. So the work of Martin in topology was exactly trying to see what does it mean for notions of topology. What do notions of topology mean in computability theory? Okay, so if you're interested in this, I can give you some. I can point you to some papers, because Martin came across these selection functions when he was looking at the notion of compactness. So his result is that a space is compact if and only if it has a computable selection function. Okay, so if it doesn't have a computable selection function, then it's not compact. And moreover, if the space is not compact, it's not going to have a computable selection function. So that's the result, the main result that I would say kind of tries to answer your question. So that's why, for instance, we know for sure that we are not going to have a selection function on the reals, because the reals is not a compact space. Brilliant.
Any other question? Is it any other question? Okay, so I'm going to stop the recording.